was something goofy going on. I just couldn't figure out what it was. Okay, are we recording?
Yes.
Are you happy? Okay.
Yes.
So, here's the point. 20 years ago, you looked in here in the index of a physics book. No mention of electrons, protons, neutrons. Talked about electricity, okay? But there's no mention of the subatomic particles 20 years ago. So all this concept is relatively new. So here was one of the great experiments that took place. It's called a double slit experiment. I'll show you what that looks like with light here in just a second. So you have what we call single slit experiments and double slit experiments. So single slit, as the name implies, you're going to shoot stuff, okay? Particles, waves, you're going to shoot stuff at a wall, and there's a single opening, okay? And you look at what happens on the other side. With the double slit experiment, as the name implies, there's two of them. And so what happens is that you get waves coming through there, and these waves can interfere with each other, and you can get constructive interference or you can get destructive interference. So what this does is that it goes through and looks at this in terms of waves, but then it ties it into electrons. So, here we go.
The granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves and radiate out, striking the back wall with the most intensity.
And that's what we call a central maximum.
With the slit.
That bright line in the middle, that's going to be what we call a central maximum.
Shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity.
And you still have that central maximum. Notice that it becomes less intense farther out because that energy is getting more spread out.
That is, matter through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern.
No, this fundamentally shocked the world of physics. They thought they had done something wrong. But no matter how they did it, they kept getting the same result.
How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge.
Even though there was just one at a time.
It's inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle.
What?
But mathematically, it's even stranger. It goes through both slits and it goes through.
That's the Heisenberg, or Schrodinger's equations of wave-particle duality. It's horrible math. I'm just telling you.
With each other.
Like one problem takes an entire page.
Baffled by this, so they decided to peek and see which slit actually goes through. They put a measuring device.
The eye is a little weird.
See which one it went through.
That's what's weird.
Oh yeah. That's what you were hung up on?
But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands.
So if you observe it,
Interference pattern of
it acts like a particle.
the very act of
If you observe it, it acts like a particle?
So if
you're not looking.
It's called
wait.
collapsing the wave function.
meant it only went through one, not both. The electron decided to act differently.
There's the one side.
Because you were looking.
He's got the big old eye there.
You gotta close your eyes,
It was here.
Yeah, what if you close your eyes?
Step forever into the strange, never world of quantum events.
Were the eyelashes necessary on that one?
Marbles are waves. And waves of what?
Yeah, I always forget what
And what does an observer have to do with
Why does he even have
any of
eyelashes?
this? The observer
What do you need eyelashes?
collapsed the wave function simply by observing.
Okay.
That was a stupid.
Is this on the test?
So you observed
No.
when you observed it, it didn't act like a wave?
Yeah, that's
Is that, like, what do you mean when why does it not?
Also, the electron literally
Isn't that
split
like
apart
the-
but went back together. So is it really
No.
one electron?
What actually splits
Like, how does
apart?
it go through two
No,
things at
no.
once?
This is what especially as you get deeper into quantum mechanics, you cannot, it is a beautiful mathematical model, and it works, okay? But you cannot overlay a macroscopic world onto what's happening on an atomic level. You won't work. All that's gonna happen is you're gonna end up in the corner, sucking your thumb in the fetal position, okay?
You know that one movie,
It
Humphrey
works
Here's the
beautifully, it's a great
That's
mathematics.
what it
Even
is.
Einstein didn't like it, because Einstein's
Yeah.
famous quote is that I can't believe that God rolls dice. And that everything is just a probability function. So, okay, now, let's go to the back
that's
room for
crazy.
just a second.
So what does it mean to change like behavior on observation? What kind of observation?
Humphrey Here's a Who. Where are we going? Where are we going? Right here? Yeah. Oh, they're so cool. Look at them.
Okay. So, what we have here is just a red laser that's shining onto a piece of aluminum foil. Now, the cool thing about lasers is, number, you can't see them, but if I do
Whoa.
this, then
Is that water?
that's just like a cleaner. Okay?
Wait, what is it?
So,
He just
here,
sprayed it
and
at
we'll
us.
spend a lot more time talking about light. So, the light is traveling between that point, okay? But you can't see it until it reflects off of something. So if you've ever seen kind of like the spy movies where they're in a room and it's got lasers, they're trying to see where the lasers are, okay? They just give that a spray with a liquid, then what's going to happen is that when that liquid is there, it's dispersing that light, then you can see it. So the photons are traveling between them, we just can't see it because they're not bouncing off of anything. So what this is, and you got to get pretty close to see this. So this is what we call a single slit experiment. So what you'll notice right
wanna
here
see.
is that there's this one bright central maximum. So as that light is coming through, okay, that bright light in the middle is what we call the central maximum. Then as you go out from that, okay, notice that you have like light and dark bands. So what's happening is that that light is coming through there and it's spreading out. okay?
Wait, can you repeat that?
Okay, so you have this bright light in the middle, so what you call a central maximum,
Yeah.
okay? So that's what's the most intense light, okay? So as that light comes out, it spreads out like a wave. And that's why as you go further and further and further away, those bands become lighter and lighter and lighter because that energy is getting more spread out, okay?
Okay.
Got that. Now, watch out. Sorry.
Wait, so which one is this one? Is this the one where it's like one one thing?
That's a single slit.
Singles? Yeah. Okay.
Okay. Now,
Oh, that's cool.
if we can move it now, I'm going to move it over.
Oh, you made little slits in there.
Oh.
Hey, Gracie.
Okay. Now, this one is a double slit experiment. Watch out, watch out.
In the way.
Now, with this one,
I don't even see him. No way.
with this
Got
one,
boxed out.
you'll notice that this doesn't have as bright of a central maximum, okay? But what you'll see is that you're going to have more defined regions of light and dark areas. Because what's happening as that light is coming through both, because light is a wave, it's acting like a wave in this situation. So as it's coming through, those dark regions there are where you're having destructive interference. Crest is meeting a trough and it's canceling each other out. Where you have the bright lines, okay, with that one, that's where you're going to have constructive interference. So as that wave comes through, because it's a double slit, so as it's coming through, this is why when you have a double slit, you don't have that, you do have like a central maximum, but it's not as defined as it is if it's a single slit experiment. Because if a single split, boom, comes in, it really doesn't interfere, it interferes, but not as much. With the double slit, that's where you get that situation where they are two waves coming through, constructive and destructive interference, and that's what's causing these bright and dark bands as you go across. So, got that idea?
Louis had a question.
Okay, Louis.
I have a question.
What?
Does it matter how far my board is from the
Louis, why are you all the way back?
It does in terms of the mathematics. It does with the math. That distance is going to be very important in terms of the math. Okay? Huh? Okay, watch out. All right, watch out.
Oh, my bad.
Bruh. I got clean.
That's so weird.
Have you guys ever done that?
Have you ever like looked into a laser? Is it really that
I'm
dangerous?
so confused. What does it mean?
Actually?
No, it's not. I'm lying to you. It's not.
That definitely doesn't call us.
Yeah, look into it.
All right.
Why did you just get so close?
I'm trying to what?
Here's the next thing. What's known as the index of refraction.
Oh, I thought we were going.
If it was after.
It can't.
Index.
It's not hooked up.
Oh. Just look it up. You're gonna figure it out.
Okay. So when you look at what we got, the speed of light, 3.00
Times 10
to the eighth meters per
Is
second.
that an 8? No way. What is that?
Kilometers.
Is that how you draw your 8s?
People draw eights
You do your 8s like that?
Ignore that. I can do that. Okay? Now, so here's the deal.
It's an SF.
So when that's what we use as the speed of light. That's what's technically in a vacuum. We'll get more into where that creates a problem later on in terms of how we get light from the sun. So when you look at this value, that's like the absolute highest speed that you can have, absolute best case scenario. One of the things we'll talk about was known as the index of refraction. The index of refraction is basically how much it slows light down. So it's, the technical term is something being optically dense, okay? So the more N, or the bigger N is, the more light slows down. Now, if you look at E equals H times frequency, if you want to go old school and go E equals H, who liked this one? Is that Louis?
Louis, I like writing those.
Louis likes the new.
New
Okay?
is cool to write.
Okay. Now, So let's talk, we'll spend a lot more time talking about this equation. But this E is the energy of one single photon. And this is what determines the color of
Height.
the light.
It's
This
just a
determines what
constant.
you see.
Is that like MC?
So what
What
allows,
happened to MC
kind
squared?
of ish, but not really. So what allows you to see this as being purple is the fact that there are certain photons that are being bounced off this thing. It basically absorbs every color but purple. And the purple gets bounced off and it hits your eye, it transfers to your optic nerve, and and your brain says, oh, that's purple. Okay? Now, but if I hold this up, like in front of this, right? Does it still appear purple?
Yes.
Yes. So what that tells me, that as that light goes through that medium, it's actually slowing down. It's slowing down as it goes through that glass. So what that tells me is that if you look at c equals the speed of light times frequency, or lambda nu, whatever that case may be. So what that tells me is that it's the frequency that determines the energy. And it's the energy that determines the color. So what that tells me is that as that light travels through this beaker, when that light hits that glass, it slows down. So what that tells me is that it still looks purple. So, thank you, Joe. That still looks purple, so what that tells me is that I'm still getting the same frequency. But the speed of light is less. It's got my laser.
Why is that going up?
I have a question.
Keaton, put it down. Come on, Keaton.
How do you know your wavelength is constant? Because it's the same color?
No. Okay. Energy is going to stay the same. Okay, whether it's in light or it goes through that glass. So my energy is staying the same because it looks purple no matter how I view it. Okay?
That's what determines the color?
Yes, it's the energy that determines the color. So as it goes through light, what that means is that the speed of light becomes a little bit less. It might be like 2.98 times 10 to the 8th meters per second, depending upon the index of refraction. So if the speed becomes less and the frequency becomes less, what has to happen to the wavelength?
Stay constant.
Excuse me, the frequency stays the same, so therefore the wavelength has to become,
Less,
Greater, smaller.
smaller?
hold on. Frequency stays the same.
And what?
Yeah.
Frequency stays the same because energy stays the same because the color stays the same.
Yeah.
So then, yeah.
So
So
wavelength
if frequency stays the
decreases?
same, but the speed of light is less, what's the only way that can happen? What has to happen?
It has to decrease.
Wavelength has to become smaller. Okay. Now,
What's the H?
H is called Planck's constant. It's just a number.
Yes, Planck.
Okay.
I
So
forgot
I'm
his
going to take
name.
this. This is just canola oil. I'm going to pour that in here.
It's zoomed out.
Okay.
I can,
So I'll give you 10 bucks.
Right?
Say?
So if you look at what's happening
Warping it.
for light to travel through there, it's actually pretty complex. So the photon has to go through the glass. So if you were to look like down on top, so the photon has to go through the glass, through the canola oil, through the Pyrex tube, through the air inside the Pyrex tube, out the Pyrex, through the oil, back through the glass, right? So there's a whole bunch of transitions that are happening with that photon, speeding it up, slowing down. Now, what I want you to do now is I want you to focus on the tube, okay? Focus on the tube.
I'm so focused right now.
Focus on the tube.
Color's gonna change.
It's gonna go.
Focus on the tube.
It's gonna go purple.
It's gonna get
It's gonna
huge.
disappear. You're not gonna see.
wow.
Oh,
That's cool.
So, yo, that's so cool.
Wow.
No way.
Wow. Oh.
That's actually sick.
What two?
No way.
Y'all can't see it.
What two?
Now, here's the deal. The reason that it disappeared is because canola oil and Pyrex have the exact same index of refraction. So what that means is that the light doesn't change any speeds as it goes through the oil, through the Pyrex, through there. Now, when there was air had a different index of refraction. So that's why that could show up. But once I filled that up with canola oil, it looked like it disappeared. Still there, right? But it's only because now that light can't tell the difference between the canola oil and the... We'll do it again just because it's good to see.
It's a lie.
It's a lie. Even now, you can see, it looks like the bottom of it,
It's gone.
it looks like it's like floating.
Oh, it is floating.
Oh, it's gone.
Uh-oh. Dito, you might not want to drink it. You might disappear, man.
And there we go. All right. Okay. Back we go.
Vito's so scared. Let's try it. Let's try it. I didn't even know he did. This man's out of soccer. I didn't know where he'd be a crazy soccer player. They don't guard him.
Can you turn that right leg was just invisible?
Oh, that's my right.
That looks trippy.
Kicking like this.
The term is called collapsing the wave function. Your wave function is given by the Greek letter psi, and it describes all the possibilities of where this thing could exist. So when you make an observation, basically, instead of having all the possibilities, it forces it to choose only one option. Okay, and then mathematically it's called collapsing the wave function. So instead of having like two different solutions, you only have one possible solution. And so that's how it works. And then that becomes psi squared, and it gets really ugly.
If you look at that sheet of aluminum foil hard enough, it collapses like.
No, stop.
There's no way they're not just making this up.
That's what I was thinking. I was like,
How do they know this?
Wasn't it like Einstein's thing where it was like, if I'm not looking at the moon, it doesn't exist or something like that?
I've never heard that.
that is so true though.
I'm making it up then.
That's how you do it. That's science.
Just make it up and then prove it later.
Yeah. Or have somebody else do the work. And then like 100 years later,
Is that a V?
completely
What's
wrong
that?
and someone
Okay.
else
And then
is-
copyright.
Which one?
So let me kind of explain what I've got going here.
Oh, that's new.
Okay?
Which is
So,
frequency.
depending upon your preference, you can either have velocity equals wavelength times frequency or the Louis lambda nu. Okay? So, this n, which is your index of refraction, there's a couple of different ways you can look at n. One is that it's going to be the speed of light measured in the vacuum divided by the velocity in the new medium. So your vacuum is your best case scenario. So space created a problem with light. And because here's the problem with this, is that if you're to hear my sound, there has to be air between you and I, and that gets transmitted through the air. So obviously we see the sun, we see the moon, we see the stars. So the idea was that in between the sun and the earth, and that filled this void, was this magical stuff called the ether, okay? And so this ether had these special properties because it could allow light to get transmitted through it, but it didn't slow down the earth or any of the planets as it moved through it. So it was there, and because we thought we had to have a medium for light to be transmitted, because we couldn't at that point understand how light could be transmitted through a vacuum. So we said, oh, it's the ether, okay? It'll work.
Did they think that it was like dark matter?
No. This is way, this is 1800 stuff. This is way before dark matter. We hadn't even figured out that there were other galaxies at this point, okay? So, this ether had to exist, and everybody didn't like it because it was like, come on, man, you have to give it all these special properties that we've never observed before, and this just doesn't make any sense. So, later on, when we get into with James Clerk's Maxwell's equations of electromagnetic radiation,
How does this make?
That's how they figured out that light can be transmitted without a medium. Because basically it's called electromagnetic radiation. The electric field creates a disturbance in the magnetic field. The magnetic field creates a disturbance in the electric field. So it becomes a self-perpetuating mode of transportation in terms of energy. So we eventually punted the ether. But when it first started, we needed that idea. Yes, Sam.
What is N again?
Huh?
What is N again?
N is the index of refraction.
Index of refraction.
Index of refraction. So yeah, I see over these. Yeah, I haven't been right.
So,
Can you circle the ones that are really important? Because I feel like it's just like everything rewritten over
and again,
again.
everybody's going to need this number.
Are we talking about H?
No. And I'm not going to expect you to know that.
That's on the equation sheet.
You will eventually. Just
Planck's
not now.
constant. Do we have to? Are these on the equation sheet? All of these equations on
Okay.
electricity?
So on page, so you all like page numbers. On page 538,
One of them over here, bro. No, he doesn't want you to use it, bro.
there's a table of indexes of refraction. Vacuum, air, water, glass, diamond. So what makes diamond so cool is that diamond has a very high index of refraction. So what that means is that when it gets into diamonds, light slows down a lot. That's what kind of gives it that shimmer, is because of the fact that it has such a high index of refraction. So here's the story. There's a couple of ways you can look at this. One is that if you know what the speed of light is, 3.00 times 10 to the 8th meters per second in a vacuum, and you divide it by what that velocity is in a new medium, that's how you can get the index of refraction, okay? So like if we knew like the speed of light in a particular medium was 2.00 times 10 to the 8th meters per second, take 3, divide it by 2, we'd have an index of refraction of 1.5, okay? That's one way you can look at the index of refraction. Now, if you do a little bit of rearranging, and this makes sense, if you know what the index of refraction is, and you want to figure out what that velocity is going to be in the new medium, take C, divide it by that index of refraction. There's the velocity in that new material. So if you look on that chart on page 538, a vacuum has an index of refraction of 1. So if you take the speed of light and divide it by 1, oddly enough, you get the speed of light. So the bigger N is, the slower light is in that material. Okay? It's called more optically dense. So it's almost like it's running into like molasses. Okay? So the light's coming along, all of a sudden, whoa, it slows way down. Okay? All right. Now, here's the other way that you can look at this.
What is that
What?
on the right of the H?
What's the thing
That's
under
new.
new?
That's new.
That's new?
Yeah.
Alright.
Or frequency, whatever you want to put down.
Yeah.
Okay?
We've been known
Now,
the way you need.
so here's the story. Here's the other way that you can look at this. Is that if you look at that index of refraction equaling C, equaling the two velocities. So that would be frequency times the wavelength in a vacuum, and frequency and the wavelength in the solid. Now, this is why things don't change color when you look at them through the glass, which would be really weird. So if the frequency changed, it would change the energy, which would change the color. So what that would mean is that, like, you might look, if you're walking outside and you're looking at the sky and, oh, it's blue. You get in your car, glass has a relatively high index of refraction, and if that light changed the frequency of, if that glass changed the frequency of that light, that would change the energy. So if you were looking through your car window at the sky, if it changed the energy, then it might look purple or it might look red. Okay? But then if you stuck your head out, oh, it'd be going back to blue again. So it'd be this really weird thing. Even if you were wearing glasses, okay? If you had your glasses off, that sign might appear red. Put your glasses back on, and if that light changed that color, changed that energy, then it would appear a different color. Okay? So thankfully, the frequency stays the same. So all I did here was a little bit of voodoo. I said, okay, this is how I can calculate the speed of light in a vacuum. Frequency times wavelength. This would be frequency times the lambda in that new solid. Now, here's the deal. Because the frequencies stay the same, those cancel out. Oh, okay, cool. So with that, the other way to look at N then is that it's the wavelength in a vacuum divided by the wavelength in the new material. So if that's the case, if you want to get an N value greater than 1, what do you know about the wavelength in the new material? It's going to be, is it going to be bigger or smaller than the wavelength in the vacuum?
Smaller than it.
It has to be smaller than. So when light travels through an optically dense material, the frequency stays the same, but the wavelength becomes smaller.
Wait.
Louis?
You can get bigger wavelengths through a material than you can in a
No.
vacuum?
Your biggest wavelength is in a vacuum.
Okay, so it has to be less than 1.
Yes.
Gotcha. Okay.
No. The index of refraction, of refraction has to be bigger than 1.
The wavelength in the vacuum.
What if it was
Oh, sorry. Yeah. Okay. Yeah, I gotcha. Sorry, I have it.
Oh, okay.
Okay, so the index of
It
refraction
has
has to be greater than or equal to 1.
Oh,
Okay? So even if the wavelengths are the same, N is going to equal 1.
So a cool material like diamond has a really low refraction number,
No, it has a really big refraction number.
so it's like really close to 1.
What
No,
does
it's
it
far
mean?
from 1.
But you're dividing one.
Okay,
I'm confused.
you're not going to change the wavelength in the vacuum. That's
So
a fixed
frequency is
value.
also always constant, right?
Huh?
Is frequency going to stay the same always?
Yes, no matter which medium it's in. The frequency is
For
going to
each
stay
color.
the same, which is why the color stays the same.
Okay. And then the wavelength, what about it?
We can change the wavelength.
Yes.
So the only way that you can get an N greater than 1 is if the wavelength in the material, right, is less than the wavelength in a vacuum.
What?
Why
What?
is it not possible?
Yeah, that's what I was saying, because you're dividing it. I'm confused.
You know.
Louis, you're confusing everyone.
1 divided
Because if
by...
you divide by a smaller number, it has to be greater than 1.
Look, let's make the math simple. Let's say the wavelength is 4. Let's say that's the wavelength in a vacuum. Okay? So if the wavelength in the material is 3, what's 4 divided by 3?
4/3.
1.33, right?
Yeah.
It's greater than 1.
So N is greater than 1.
Yeah. Sorry, it's just a lot of information, you know?
But you got it.
Well, I hope so.
Okay.
Recording? Is it recording?
Yes, it's recording.
More good.
What if N equals 5, which is
Not
possible?
possible.
If the wavelength is 5, excuse me, then N becomes less than, which would mean it would go faster than the speed of light in the material, which isn't possible.
What if that makes sense?
Okay? Louis?
So can light travel through? This might be dumb. Can light travel through solid objects?
Travels through glass all the time.
No, like more solid object. Like a wall. Get past the
Like, what's more solid than glass? Hit the glass, I tell you.
The solid,
Hit back. Whoa! Oh, that was rubber, it bounces back.
I know what you're saying.
So like even like a little bit comes through, but it's got such a
Yeah.
low
That's something else, isn't it? That's
refraction.
passive.
No.
Then how does it not go through the wall?
What about the
So here's what, when light,
Why does it not go through the wall?
hold on,
absorbent? 5%. That's why it's colorful.
hold on, just hold on. Okay?
That's colors work.
Hold on. So let's say that you have a black t-shirt. Pop, you have a black t-shirt, right? So coming out of these lights, you have the entire spectrum of colors. Roy G. Biv, right?
Oh, what you did?
So you're wearing a black t-shirt. So what's happening is that it's absorbing most of that light. And that's why it appears as being a black. Okay?
Yeah.
Now, hold on, let me go get one thing. I'll show you the difference.
Look at this. Look at what you've done, man. Look at what you've done.
He's asking good questions.
Oh, we've made him go into the room of despair.
What?
We don't know what's in there. We're not allowed in that room.
I've been in that room.
We're not allowed in there. Heathens.
Oh, are you gonna hit someone with that?
Yeah. That's the late word ball.
Yeah, Louis, come here.
Ooey.
I was only a day late. I didn't.
Ooh, we go
I
up
was
there.
understanding. I didn't think you cared.
Okay.
Whoa.
No way.
Whoa.
That's
Ball.
So what does it look like?
Look, there's like
Like a
different color in there.
It looks
It
like
looks like a
sun.
white light, right?
Oh, it looks colorful to me.
Whoa, what are you doing?
That's trippy.
Don't
What's
let
on
go.
my eyes?
Now what does it look like?
It's
a
rainbow.
Red. Looks like 3
I don't
balls.
see it.
3D image.
It looks colorful right now, though.
Holographic.
Okay? But
Red, blue,
You can't see the light?
Like a little bit, but not.
It looks like 3 distinct balls.
red, blue, and
looks
green.
red, blue,
Is
and
it because there's different
Green.
wavelengths?
yes.
Oh my
And
gosh.
Okay?
Good job,
So
Harana.
white light is a blend of those colors.
Yeah.
So when something appears white, what it's doing is that it's reflecting off all of those colors. When something appears black, it's absorbing that energy, that light, and it's not reflecting it off. This is why on a hot day, you don't want to wear a black t-shirt. Why? If you're out in the sun.
Because it
So
absorbs
it's
all
all
the
the light.
It's going to absorb that energy. You want to wear light-colored clothing.
Ah.
Now, if something appears like my white shirt, this appears white because of the fact that it's reflecting all of those colors. Now, let's say that you have a red chair, okay? Here's the anomaly of a red chair. That red chair appears red because it absorbs every color but red. And red is what gets reflected off
I
of
know
it.
how that works.
So what that would mean is if we had lights that didn't have red in it, okay? If we had lights that didn't have red light in that spectrum, that chair would appear black. Because there would be no red light to reflect off of it.
Oh, that's why dogs can only see certain colors.
Well, just because
Because they're retina, right?
well, that's
Where does
just
this come from?
so what you see as white light is actually a blend of different
I can
colors.
see everything.
Okay.
when it's off to the side.
So that was one of the ideas that supported the idea that light is made up of a blend of waves because of the fact that you can separate them out
Dude, I know.
based upon those wavelengths. And that's what Isaac Newton did with his prism.
Wait,
Okay, what?
but why does it like go through glass, but it doesn't go through the wall?
Okay, here's the reason why. This is,
Yeah, that's a good question.
No, you
oh, no, it's a
you're-
valid question.
What's glass? It's sand. So what's that made of?
I play
Sand,
I know, but what's sand made of?
rocks.
So typically mostly silicon dioxide.
Silicone dioxide?
So
Oh
here's,
yeah, 'cause
here's,
Minecraft. It's
Pop, here's the
silicone.
short version.
Yeah.
Okay, so here's a piece of glass. And here comes this photon as it comes through it.
Yeah.
So basically what allows you to see anything that's clear is the fact that as that photon passes through, there's nothing to interfere with it. And it just keeps going through. Okay? So that's why I can put my eyeball over here with the eyelashes just to flick you all out. Okay? Right? So what's going to happen is that photon makes it through the light because it doesn't interact with the electrons that make up that material.
Okay.
Now, if you have a wall, and let's say that that wall was painted red, okay? That same photon hits that wall. So what's going to happen on an atomic level there is that those electrons are going to absorb that spectrum. except for what we have deemed as human beings to call red light. So that red light is going to bounce off of it. All the other ones are going to get absorbed by it. Okay? So that's the difference between what happens with glass and what happens with
So
wall.
there's no interference with glass?
Yes, those photons just, they act like they're not there.
Okay.
That's why. Because there's nothing to absorb those photons.
There's no charge on it, is that why?
Oh, no, well, that goes back to the standard model, and that's a whole other discussion too.
Does
But
that
yeah.
have, does that have anything to do with like the refraction thing?
No more
or-
questions.
Well, it kind of did. So
or
what
the
happened
double thing, the double whatever wave?
is that when you had, or you're combining three different things, okay? So when you had that tube, right, and when it was empty, those photons hit the glass, they slowed down. Hit the oil, slowed down some more, hit the Pyrex tube, changed speed, hit the air, sped back up, then exited. So when that tube was in there full of air, you could see it because of the fact that those photons were interacting differently with those materials. Now, you come in here and you say, okay, well, let's fill that up with canol.
Wait, I thought you said you can't use different in an answer.
I can.
Increase and decrease. That's
Okay.
your word.
No. I replaced the air
Yeah.
with something that had an index of refraction that matched the
Oh,
oil
yeah.
and
So,
the Pyrex.
So it never changed speed. That's
Yes.
what
So it just traveled through and it couldn't tell the difference.
you're saying. Okay.
why can we see it if it starts in the oil and ends in the oil? Wouldn't it just, I guess it would change, but that frequency.
But some
wouldn't
of
make it
that
to
some
us.
of that light energy is being reflected out,
Wait,
and that's how you can see it.
It makes it through the oil?
Yes, some
How
of
come
it
doesn't
does.
change?
you said it doesn't change speed that whole time?
When it enters, it
If
doesn't.
you fill it up with oil, it doesn't change speed.
Oh, okay.
But if there's air inside, then it does change speeds.
Okay.
Okay, so it's like always speeding up or slowing down. But if it's all the same medium, then the light can't tell the difference. Now, here's the weird thing. Okay, I'm reluctant to tell you all this.
Maybe don't.
Do it. Tell us.
No, you gotta say it. Tell us.
Well, it's the mechanism that allows light to speed up.
Are we gonna like start throwing up? Or
No. The worst that can happen is that you would just contemplate the universe a little bit deeper. But yeah, so, okay, hey, light speeds up. F equals ma.
Yeah.
What's the force that makes it speed up? The easy part is when it slows down. Oh, right, it's like driving your car through mud or a snowdrift. Oh, it slows down. Cool.
Is it like
Comes out of that and it speeds back up.
Elasticity.
What's the mechanism that makes it speed back up?
Elasticity.
Kind of.
Kind of?
Okay, kind of. Okay. All right, in the name of time, I got to get through a couple more equations.
No more questions. No more questions. See, these scientists are just making stuff up. For real.
Yeah.
I'm convinced.
How do you think I've made a living for 30 some odd years on 2 continents?
By convincing us.
Yep.
Brainwashing us.
I get you all to drink the Kool-Aid.
Yeah.
This is
You
just
are a
another
good
name for
salesman, Mr. Steven. You could sell me a car any day.
I mean, think about it.
No.
It's like the, what's it, the Illuminati?
No, I'm kidding.
The Illuminati?
The government wouldn't do that,
What is what?
but they
That's
would.
crazy how
Do
they
that?
something dumb.
They would.
You know that TikTok?
No, that's what I'm saying. Like, honestly,
Yeah,
is
how do we know
anything
we
even
don't know
real?
other things, Mr. Burkham? How do we know we're not going to discover something else about this stuff?
We don't. That's the beauty of it.
That's not the beauty of it.
the great thing
Because you discover one thing, trying to discover another thing.
Yeah, but what happens when it ruins? Like, what happens if we find out gravity it doesn't exist and it ruins every single equation we've ever made in the whole entirety of like the universe?
Then I guess we get back to work.
Well, that's the problem with dark matter is like we're missing like 90% of the universe right now, and it's kind of embarrassing.
What if gravity just
Do
wasn't
better.
real? What if we discovered that?
What?
Now, it has to exist. Otherwise, we wouldn't be here having this discussion.
That's all I do. It's just like an achievement.
Easy move.
All you see is a
You could do freestyle mode on the roll.
Freestyle
mode.
That's fine.
Y
Creative
in.
mode. You can choose whatever character you want.
Okay. So, what this equation gives you,
I don't like
Okay.
that.
Which is why I don't even
hold
know any
on,
of those.
just chill out.
Getting there.
L is length.
No,
Yes.
L is angular momentum.
Good, bro. Ooh, let him good. Einstein.
Okay, so
Should have held it back.
you got y equals m lambda L over d. So this works on as long as you have a double slit experiment. So
Over what?
m is what we call almost like the harmonic. So what's going to happen is that here you have like a light source, and it's shining this light through this double slit. So these waves are going to come through, and they're going to interfere with each other. So in the middle, you're going to have that central maximum, that brightest part. Okay, so you can have that right there. So then you're going to have some dark fringes and bright, and it's going to alternate dark, bright, dark, bright. And they're going to get weaker and weaker and weaker as you go because that energy is getting more and more spread out. So what the M tells you is basically it's almost like the harmonic. Is that the first harmonic, which means it's the one closest to the central maximum, is that M equals 2, which would be the second one out. So unless you're specifically told differently, you assume that M equals 1. Okay, so unless you're told, oh, it's the second harmonic or the third harmonic, don't even worry about M. Okay? Now, lambda is the wavelength of whatever that light is, or sound, it could be sound as well. L is the distance from the screen to the board, and D is the distance between the slots in the material. Okay? So, and then this is going to get you how far apart these are. So if you look at light, visible light, okay? Light has an extremely short wavelength. Nothing that we could measure, because number one, it would be horrible. Because if you think about it, you're trying to measure the speed of light, which is really fast, and then you're going to try and measure the wavelength of that light as it's moving, and it's like 10 to the negative 6, 10 to the negative 8 meters. So you're going to try and measure something that's traveling at the speed of light that's, 1,000,000 times thinner than a human hair. Good luck with that. So what we do is we got this clever little experiment. So what we can measure is we can set up a deal like I just did with the laser. Oh, I can measure the distance between the two slots. Oh, I can get that. Okay, got that one. I can measure how far apart the screen is to the source. Okay, I can measure that. I can look at the spectrum, and I can measure how far apart those little fringes were. I can measure that. So the only thing I don't know is the wavelength of the light. So this is a cool way to measure the wavelength of light without trying to directly measure the wavelength of light.
How do we know that?
So, let's look at this. This is where things kind of become a big idea. Let's say that you're going to do this experiment in air. Okay? Got the distance here, central maximum, all this good stuff. We're going to take that same apparatus and we're going to submerge it in water. Okay? What's that going to do to the distance between the two slots?
Stay the same?
Nothing. What's that going to do to L?
Nothing.
Nothing. But what's it going to do to the wavelength?
Decrease.
Wavelength is going to become smaller.
Smaller.
So if the wavelength becomes smaller, what's that going to happen to the distance between the fringes? That's going to become smaller. Okay?
Wait, how do you know wavelength
Yes.
becomes smaller though?
Because
Just
in water, it's going to slow down.
Oh, it's slower?
Yeah.
Why?
But sound is faster, right?
Yeah, I
Sound
thought.
is faster.
I
Wait,
thought
light
water.
is
Oh, light. Yes.
Light.
Oh, yeah.
Yes,
Sound
this is
faster.
light.
Yeah.
Okay?
Wait,
Now-
what about frequency? So does frequency just always stay the same or something?
Yes.
Then? Always.
Always. With light, it always stays the same.
Okay,
As long as the energy is staying the same.
but with
Wait.
sound it changes.
So
Now,
is there like an accepted value for it, or do
for
we
what?
for the
For each
frequency?
color, yeah.
For each color.
Oh, really?
Yes.
Okay.
Can we change the frequency enough to where the color just disappears?
What?
You can't change frequency.
Like for us, I mean.
Stop asking questions, Louis.
My brother.
Let the man teach.
My brother.
Hold on.
Don't let him cook.
Who let him? No. Don't start with that. No,
Now,
no.
here's a different way of seeing how those bright lines appear. So here's this double slit. You have this light coming in here like this. So the light's going to come through here and it's going to travel a certain distance. Then that light's going to come through here. Well, which light's going to travel a greater distance? The one that goes through the top or the one that goes through the bottom?
Top one.
Top one, right? So what's going to happen is that this, where these occur, so you've got this and this, this and this. So the differences where those maximums occur always have to be a multiple of the wavelength. That's why you have M. Okay? So those are going to be spaced out by a multiple of the wavelength. Jackson?
Is that the same thing with like different harmonics? Like with frequency and sound?
Kinda-ish, but same idea.
Wait, so
Yeah.
what is M?
Yeah, I'm confused on what this.
M is just, you would have to be told, like, which band of light are you looking at? Are you looking, if M is going to equal 1 when it's the band of light closest to the central maximum.
Okay,
M
it's
equals
like
2, well, like if you had something like this is how it would appear. Let me change this color for a second.
I guess so. So it's like how far out you're looking.
So imagine this.
Yeah.
So you had something like this, Louis.
Uh-huh.
That's what you saw with the double slit experiment. So this right here would be M equals 1.
Wait, that was the double?
Yes,
Yes.
this is a double.
The two slits.
Because you still got a central maximum. Okay?
Oh, I got you. Okay.
And then over here, this would be M equals 2. This one out here would be M equals 3.
So from the first to the second is M equals 1, the second to the third is M equals 2.
Yes.
third to the, okay.
Yeah.
Oh, it's
So
the space in between.
you would have to be told, like, hey, if M equals 2, then what would be the difference between the central maximum and
But
the
it
next
wouldn't
band
matter
of
anyways,
light?
it's the same distance, right?
Huh?
It's the same distance?
No, but if M equals 2, these are the same distances, but it would be like doubling. So if M equals 1, it's the distance from the central maximum to this first fringe. If M equals 2, it would be twice the distance.
Oh, it's always from the central maximum?
Yes, it's always
Oh, I
from the
got you.
central maximum.
Okay.
It's always from the central
It
maximum.
doesn't just move?
You could have M equals 14, and it'd be way out there.
Gotcha.
Okay? Got that. Okay, got that, got that, got that. Okay.
Right mind.
Homework. Now, the good news is, literally, this is all it took me to do. Okay?
I don't think that's how it works. Why should I want to know if that's
It
how?
would.
I don't think Mr. Burkhead can even answer.
It's gonna be the biggest central.
Is there gonna be a lot of conceptual stuff on the test?
Yeah.
Okay, can we talk about that tomorrow?
They come all the way back around. Like that? Like you're doing the experiment, you like have one all the way around the earth, and it just keeps going like further around. You mean, and it wraps it all the way around. All the way around the earth.
What is all the way around the
Like
The maximum.
like the earth.
Maximum.
Pretend this is the earth, like the round head. Like the thing wraps all the way around it. And you just keep no, you're doing that experiment, and the maximums keep spreading out more, you know. And then you just keep going further and further around the earth, and it just slowly wraps around it, and then comes back around or something.
Yeah.
Yeah, exactly.
Okay. Cool. That's good. That's good. Yeah.
That's Vitor's question.
That's my theory.
Okay.
Publish this now.
Oh dear.
I already know this assignment.
Oh, there's more?
How many days left to school? A few.
The D sign for that?
He's almost May.
No, we have 15 weeks.
No.
Okay, there you go.
I know.
This is another equation that's in your book. This is basically the geometry, and I'll go through the geometry and why that works tomorrow, but you're gonna need that on number 7. They're gonna ask this for radians and degrees, just give it in degrees. It'll make sense when you get there. When you get to question 7, just A through C,
M is that distance deal, right?
Yes.
So it's gonna be 1.
unless you're told differently, assume that it's 1.